Okay. So I'm pretty much going to finish your notes today. I'm going to give you guys a few more notes by email on steady state approximations because I do want to cover those just a little bit. The problem with steady state approximations is the good examples require more algebra than I need you guys to do, but I do need you to understand the concept of how it's put together. Okay, we were talking about the collision model, and we've already kind of alluded to this when we talked about the kinetic molecular theory. And there are some different things that would cause a reaction to happen. I erase all my ink. First off, molecules have to collide. That is our current theory right now, that molecules collide to make a reaction happen. The collision must first provide enough activation energy to make that happen. The second thing is temperature. If you increase the temperature, clearly you're going to have more molecules with a sufficient amount of kinetic energy that they will collide hard enough to break and reform bonds. And that's all this. Hold on, I need to minimize that. Hide. Ugh, stupid computer. Pardon me while Norton's having technical difficulties. Oh, come on. And now I'm yelling at it. There we go. You can go wait. No, you guys, that or whatever. Okay, so if you take a look at this graph, this is just the chance of a particle that has enough kinetic energy to react. If you remember, temperature is measured by the average kinetic energy available to all the molecules within a particular substance. If we increase the temperature, which is what red is, red means increase in temperature, which is kind of funny if you think about the stars, but we'll go with it. If we increase the energy, the activation energy does not change. That is a threshold. That is a bar. You're never going to get the molecules to react no matter what the temperature is until they cross that threshold. That value does not change. What does change when you increase the temperature is what? I'll repeat it. Number one, increasing the temperature does not change the activation energy threshold. What does increasing the temperature cause?
It would increase the probability that you reach the threshold by, well.
Yes, but what's going on? For those of you of calculus, look under the curve. Does pre-calc talk about the area under the curve? Just out of curiosity. Okay. What do you notice about the area under the curve versus the red line versus the blue line? And the area under the curve of the red line versus the blue line. What's the difference?
The red is bigger.
What do you mean bigger?
Like more area.
Okay. So for the red line, we have a larger area under the curve. Which, as Daryl correctly stated, you end up with more particles over the activation energy threshold. So increasing the temperature will get more molecules over that threshold, so more will react. Increasing the temperature will not change the activation energy required. It just pushes more molecules across that finish line as it increases the area under the curve.
I have a question.
Yeah.
Is activation energy like the energy required in the total system to react, or like kinetic energy of each particles to react?
Ooh, that's a good question. It's that of each particle as you go from reactants to products. So it's the energy to get the reactants to the products in a single system, in a single chemical equation.
So like
Yeah.
some particles might have enough energy and react while some might not.
Say that again.
So like some particles might have enough energy to react, but some might not.
Yes, yes, since temperature is based on the average kinetic energy. You know, some of them are going to have enough average kinetic energy to collide with enough force to break and reform bonds, and others will not. As you increase the temperature, you're going to increase the probability that more of those molecules will be able to cross that threshold. Good question. And the one constant was 0.08206. What's up with this 8.3145? Wendy?
I don't really remember, but isn't the same thing?
They are the same. There's some loud beeping going on over there. They are the same. How can they be the same? They're not the same number. Missy?
Different units.
Yeah, they have different units. Who's got the, Lincoln gave them to me before. Who's got the units of our? Lincoln, I was right, it was you, right?
I think.
Did somebody other than Lincoln say something? Patty, you want to give it a go?
Pass.
Patty, before I let you pass, what's the ideal gas law equation?
PV equals nRT.
You want to take a stab at the units now, or do